So the next step here on this problem is to break it up into pieces. So what we'd like to do here would be to draw up free body diagrams of each of the pieces. So we've got ACD, and then we've got BDE. So let's have a look. All right, now if we have a look at ACD, that would look something like that. So we would have the pin joint up there at A. So that would have two reactions on it. And then what we would do would be to look at this pin here that's holding the pulley in. And as I mentioned earlier, we take those cable forces and put them at the pin. So normally, rather than using these pulleys with their dimensions on them to figure out where those cables are coming in, it's easier just to put the cable forces at the pin. So that would look something like that. And then, of course, we'd have the forces at D as well. So got those down and right, it looks like. So I'll mismatch that. So we'd have these pin joint forces there at D. So that would get us a free body diagram of that diagonal piece there. Okay, so that would look something like what you see right here. All right, now the horizontal piece, we're going to have to pay a little bit of attention to this one. We're going to want to draw a free body diagram. So that I would probably go with something like that. Now, if we look at point E, what we've got there is the downward load caused by this first cable. So that would be 600 there. But then we also, as we cut this free body diagram, what we're getting is that downward cable there that I've moved up to E. But we've also got these two cable forces that are caused as the cable wraps up and around like that. Okay, so I'm going to have to move both of those to the pin, so they're going to look something like that. So at E, I'm going to have two downward forces of 600 newtons plus a force to the left of 600 newtons. So the one that I'm showing over here, that comes directly from this downward cable. But also I'm considering these two forces on the pulley. So I'm transferring those over to E as well. So I've got one to the left at 600, and then actually it turns out two downward at 600. Okay. Now I'll go ahead and draw my free body diagram around that horizontal member there. So I'll have these reactions at B, and I'll also have reactions at D, which will go the opposite directions from the ones that I've drawn. And that'll be caused by the pin at D. Now the pulley on the angled member there, I think it's ACD, I don't have to consider that because that's not really part of this free body diagram. Even though it looks like I'm drawing kind of around that and doing some things with that with my boundary around the horizontal member there, I'm not really cutting through that stuff. So really all that I'm cutting through is this member right here to isolate the pin joint right there. That's really all that I'm doing. I don't have to concern myself with that downward 600 Newton load because that's really attached to the pulley up above. So I'm not really cutting through that as I isolate that horizontal member. So when I isolate the horizontal member, what I've got are the two reactions at B, Bx and By, the two at D, which I show in the opposite direction of the two that I found that I have on the angled member there. So what I'm getting at there is I've got dx to the right, dy down. Here I've got dy up and dy to the left. Okay, and then at E I have two 600 newtons forces down, and then one to the left. So there's my free body diagram of the horizontal member. So once I have those free body diagrams drawn, I'll just take a moment about B for the horizontal member and solve for dy. I'll remember to turn it around and then put it on the angled member there down below, and then take a moment about A and solve for dx. So that would be dy and dx. Okay. Now for the last one here, I just want to find the force in the cable. Now just to confirm that it is just one cable, because these cable diagrams can get a little bit complicated, I'll just track it around. And sure enough, that's just one cable. Now to find the force in it, this is a statics problem, so there's no acceleration. So the force in the cable is the same everywhere. Okay, so that's one cable. It'll have one force because there's no accelerations. And we're assuming frictionless pulleys and that sort of thing. So everywhere in that cable is the same force. So I can just cut a free body diagram. And that one weight there is 600 newtons. So, and remember, when you cut through cables, what they do is they always pull. So that could be pulling up like that. Now, if I wished, I could go with a bigger free body diagram like that. And see, that would double the weight, of course, because I'm now covering both weights with that free body diagram, but I'm doubling the number of cables. So you can come up with the force in the cable pretty readily, I think, by doing that. All right, so there's the homework that's coming due.